So we see that we have two expressions for the pressure difference between here and here. One based on the exit velocity, square root of 2gh, in the continuity equation, giving us the difference in velocities at the same height between this tube and this tube. And that's this expression. And this expression here for rho gh delta y. The change in pressure should be rho gh times the delta y here. And that should be the difference in pressures between these altitudes, ignoring the small difference in altitude of the water in one tube versus the other. That really doesn't make much difference. So if we set those two expressions for the pressure equal, we get this equation. And we're going to now do just a little bit of algebra on this equation and see what we can conclude. Okay, so we rewrite the equation as you see. Back up just a little bit more so we can get a good view of it. Same equation. We're going to solve this equation for delta y and simplify what we get just a little bit. If we multiply both sides by 2 to get rid of that 1/2 and also divide by rho, which is common to every term, the rho's will go away. We'll end up with the 2 on this side. That's a fairly simple step. And then we divide by 2g. Now, when we do that, I've actually skipped a step here. No, take it back. I haven't skipped a step at this point. Okay, going to in a minute. Divide by the 2g. Dividing by 2 gives us the 1/2. We got it divided by g over here. Now, knowing that the exit velocity is the square root of 2gh, we substitute the square root of 2gh here. When we square it, we just get a 2gh. Half of that is going to give us a g delta h. I say 2gh, it's 2g delta h. We get a g delta h here. And of course we have a g that we're dividing by here, so g divides out. And we see that delta y is just going to be delta h times this term. Now let's look at what these things are telling us. Delta h is the original depth of water in the large tube, the depth that we kept the water in the large tube. Delta y is the difference in the depths of the water, or the levels of the water, in the two small tubes. And D2 and D1 are the diameters of the two tubes. D2 being the diameter of the tube at exit, and D1 the diameter of the tube that fits into that, or that one fits into. And we'll see how those numbers work here in a minute when we go back to the picture. Okay, in terms of the picture, we just solved for delta y and found that it was delta h times 1 minus d2 over d1 quantity to the fourth. Again, looking at what these are, here's your delta h, here's your delta y, which is equal to this. Here's diameter d1, diameter d2. Okay? So d2 over d1, since the diameter here is less than here, is less than 1. We're going to take that to the fourth power. That's just the power that came out of the equation when we solved it. When we did the algebra, that popped out at us. Okay, and again, we're assuming exit velocity v equal 2g delta h. I didn't write the delta here, and I'm not being really consistent about that. H and delta h are apparently being used interchangeably here. It's not a good idea, but as long as you're warned about it, I don't think it'll be too much of a distraction. Okay, now we had delta h equal 18 centimeters with a question mark. We kind of crossed that out because we weren't sure exactly what we had here. But our delta y we did observe to be 12 centimeters. We thought delta h was 18 centimeters. That was our estimate. But if delta y is 12 centimeters and d1 is 1.6, d2 is 1.2 centimeters, now these numbers differ from the ones that we started with. We used two different tubes when we actually ran this experiment, and we ran the experiment after doing the analysis. So it turned out that these diameters worked better than the others, just as far as being able to get good observations in the system. We observed a flow range of 70 centimeters from a height of 70 centimeters. That is, the end of the tube was 70 centimeters above a level floor, and the water stream went 70 centimeters before it hit the floor, 70 centimeters in the horizontal direction. Using exit velocity of the square root of 2g delta h, we get about 1.9 meters per second. V1 will be then that exit velocity times the square of the ratio of the diameters, and that'll be about 0.55 of V2, or about 1 meter per second. Okay, for this V1 and V2, the difference in our kinetic energy terms, the 1/2 rho V2 squared minus 1/2 rho V1 squared, is about 1,300 pascals. 1,300 pascals corresponds to an altitude change of roughly 13 centimeters. So that the pressure here should be equivalent to about a 13 centimeter water depth. Note that the delta Y that we observed was 12 centimeters. That compares rather well with what this is telling us. Also, if delta H, well, if the delta Y is 12 centimeters, then with these diameters, we predict that delta H should be about 18 centimeters, so that our tentative observation over here, the 18 centimeter depth with a question mark, turns out to be pretty well confirmed by this relationship. Now note that this relationship doesn't depend on exit velocity or anything. The 1,300 pascals does depend on the exit velocity. And we get a somewhat different exit velocity if we treat the water stream as a projectile. Remember that the exit velocity that we get from Bernoulli's equation is ideal, not taking into account any dissipation. The exit velocity we get here, should be closer to what we actually observe. So we could use this information rather than Bernoulli's equation to find our exit velocity V2, and then we could reanalyze this and see how much difference that makes in the predicted height of the water column, and see how consistent that is with our observations.